Okay, part 2, practice abstract algebra final exam number 6. So we have phi equals this z cross z, and go to that z, so 12, and by phi of ab equals 5a plus 8b mod 12. Part A, prove that phi is a homomorphism. So group homomorphisms problem. So for part A, AB, CD belongs to Z cross Z. Then phi of this A comma B plus C comma D equals phi of A plus C comma B plus D. And now this would be 5 times A plus C plus 8 times quantity B plus D mod 12 equals 5A plus 8B plus 5C plus 8D, quantity of that, mod 12. And that equals phi A comma B plus phi C comma D. Thus, we could say phi is a homomorphism. Part B, determine the kernel of phi. So the kernel consists of all AB such that 5A plus 8b is congruent to that mod 12, and since 5 inverse is congruent to 5 here, mod 12, we multiply by 5 here. A plus 40b congruent to 0 mod 12. Since 40 is congruent to 4 mod 12, a plus 4b congruent 0 is congruent to 0 mod 12 here. So this kernel phi equals the following set. Okay, and equivalently, A equals negative 4b plus 12k, so at A comma B equals k, 12 comma 0 plus B negative 4 comma 1, and that kernel here equals the following. The kernel is generated by the 12 comma 0 negative 4 comma 1. So moving along to part C, we want to determine this image of phi. So the image is generated by 5 and 8 and Z12, and since GCD 5, 8, 12 equals 1, the image is all of Z12. So the image phi equals Z12. All right, and for part D, apply the first isomorphism theorem. So applying that first isomorphism theorem, that Z cross Z over that kernel phi is an isomorphism of the image of phi. So since this image Z mod 12, Z12, Z cross Z, that kernel there, quotient group, should say quotient group Z cross, this quotient group of Z cross Z, kernel phi here is an isomorphism to Z mod Z12. Okay. All right, so that's for number 6. Moving along to number 7. So R equals Z15 there. Part A, find all units of R. Whoops, sorry about that. Let me just switch these. So sorry about that. Okay, so consider the following. R equals Z15. Find all units of R for part A. So this is, this is ring theory. So our units, here's our element here. Okay, A and is in Z15 and is a unit of GCD. A comma 15 equals 1, and the units are 1, 2, 4, 7, 8, 11, 13, and 14. Okay, part B, we want to get the zero divisors of R. So for part B, the zero divisors, the non-zero divisors are the non-zero elements not relatively prime to 15. So that's going to be 3, 5, 6, 9, 10, and 12. If one uses the convention that 0 is allowed as a zero divisor, then 0 may also be included. That's just a note to that. Letter C, determine whether R is an integral domain. Nope. Example, 3 times 5 equals 15, congruent to 0 mod 15, but neither 3 nor 5 is 0 in Z15. And D, determine all idempotent elements. X squared equals X. So we solve here, X squared equals X mod 15, and equivalently X times this X minus 1 congruent to 0 mod 15. From the Chinese remainder theorem, the Z15 here isomorphic to Z3 cross Z5. So it's an isomorphic to that. And idempotent must be idempotent module 3 and module 5. And in a field, the only idempotents are 0 and 1. And 4 possibilities here: X mod 3, X mod 5 belongs to the 0, 1 cross 0, 1, and they correspond to the following: here, 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 and here. So we get for the idempotents 0, 1, 6, and 10. Okay, so that's for number 7. Let's move along to number 8. Let's see if this holds up. So here, all right, Q adjoin X over Q adjoin X, consider X to the 4th minus 5X squared plus 4. Part A, factor completely. Well, we just polynomial rings problem after factoring here. We get f of x is x minus 1 times x plus 1, x minus 2 times x plus 2. Part B, determine whether f of x is irreducible over that Q. No, it factors into non-constant polynomials over Q. Part C, factor f of x over all real numbers. The same factorization works over all real numbers. And factor f of x over complex numbers. The same factorization works over complex. Okay, so that's number 8. I know I'm going through these rather quickly. Pardon me if I miscommunicate anything. So from here, number 9, let alpha equal cube root of 2. Part A, find the minimal polynomial of alpha over Q. Okay, field extensions problem. So since alpha cubed is 2, alpha is a root of x cubed minus 2. We claim x cubed minus 2 is irreducible over Q, and by rational root theorem, any rational root must be 1 of plus or minus 1 plus or minus 2. However, 1 cubed minus 2 is negative 1, negative 1 cubed minus 2 is negative 3, 2 cubed minus 2 is 6, and negative 2 cubed minus 2 is negative 10. So there is no rational root. A cubic polynomial over a field is reducible if and only if it has a root. Therefore, x cubed minus 2 is irreducible over Q. The minimal polynomial is x cubed minus 2. Okay. Part B, determine the following. And for part B, we could say the degree of extension is the degree of the minimal polynomial, which happens to be 3. Sorry about the way I drew the Q's. Part C, express that 1 plus alpha squared in that basis, that 1 alpha squared. So for part C, 1 plus alpha, that quantity squared, expanding that as alpha squared plus 2 alpha plus 1. And this is already in the basis 1 alpha squared. So we just get the following here. And for part D, determine whether that Q alpha is a splitting field of its minimal polynomial, and we could say no. The polynomial x cubed minus 2 has roots alpha, omega alpha, and omega squared alpha, where omega equals e to the 2 pi I over 3. However, we get the following there for that subset of, so Q alpha is a subset of all real numbers, and since alpha is real, the other 2 roots are complex non-real numbers. Therefore, they are not in that Q alpha. Okay, so that's number 9. And let's see, number 10. So let F equal FQ. here. Explain why f exists. Okay, so finite fields problem. A finite field of order p to the n exists for every prime p and positive integer n. And since 9 equals 3 squared, there exists a finite field with 9 elements. F9 exists because 9 equals 3 squared. Okay, part B, construct this f as the following. Well, part B, irreducible quadratic polynomial over f3. For p of x equals x squared plus 1, we check the roots in that f3, 0, 1, 2 set. And then p of 0 equals 1 cannot equal 0. P of 1 equals 2 cannot equal 0. P of 2 equals 4 plus 1 equals 5 is congruent to that mod 3. So x squared plus 1 has no root in f3. Since it is quadratic, it is irreducible. And we get that f9 isomorphic here to that f3 adjoin x and over that the quotient here over that x squared plus 1. And if we let beta equal x plus that quantity x squared plus 1, beta squared equals -1 equals 2. It's in f9. And sorry if I mispronounced anything. I know I'm going fast. Just trying to get you through this. You have it as a reference. Part C, prove that the multiplicative group f cross is cyclic. So the multiplicative group of a finite field is always cyclic. Here for this, this fx equals 9 minus 1, 8 equals 8. So therefore, it's isomorphic to z8. So that f cross is cyclic of order 8. Okay, so this order of f cross. And a concrete generator is 1 plus beta. So if we check here and we substitute, we're going to get the following, and the order is 8. Hence 1 plus beta generates that f cross. And part D, determine the order of every possible non-zero element. For part D, since f cross here isomorphic to z8, the possible orders are the divisors of 8, 1, 2, 4, and 8. So, so we wind up with the following here. 1 has order 1, phi of 2 equals that 1 element has order 2. That phi of 4 equals 2 elements have order 4. And that phi of 8 is 4 elements have order 8. Okay, so my apologies for misreading or miscommunicating anything. That was part 2. Part 3 is next. Thank you and have a great day.